So we're going to start off the lesson today looking at some basic factoring. Factoring a number basically just means taking that number and then writing it as a product of two other numbers. So writing it as some number times another number. For example, I could rewrite 10, of course, as 2 times 5. Right, so this is what we call the factorization of the number. I took the number and I reduced it to 2 more factors. What you're going to have to do on your homework is come up with as many of these pairs of factors as you can. And in fact, we're going to end up calling them factor pairs. So for example, again, if I gave you the number 10, and we're looking for all of the factor pairs of 10, well, we could definitely rewrite this as 2 times 5. But we could also write this as 1 times 10. That would also be a factor pair. And in fact, for 10, this is as much as we can do. There's no other factorizations of 10 into whole numbers. If we went into fractions, of course, we can find some more ways to multiply this. But just with whole numbers, for both of the factors, these are the 2 factor pairs. So whenever you actually have to enter this into your homework, I believe it asks you to enter it with a comma, and it will look something like this. Now, of course, in this class, you could use the x for multiplication. You'll start seeing more and more that we're going to use a dot for multiplication. So if you see me use the dot, of course, that means the same thing. The whole reason is because as we start to use x more when we get into solving equations, we don't want to confuse x with multiplication. We'll actually start using the letter x, and so we don't want to confuse the two. So you'll probably see me use the dot, and if you're not used to that notation, that's what it means. So a couple more examples of these factor pairs. I could go with maybe a larger number, something like 32. And I want to find all the factor pairs of 32. Now, of course, you can always get a factor pair by taking 1 times whatever number you're using. So in this case, 1 times 32. That will always be a factor pair. 1 times whatever the number is, because by multiplying by 1, you don't change anything, of course. But for this one, I think I will probably have some more. In fact, 2 divides into 32, so that means that I should be able to get a factor pair using 2. And in fact, 2 times 16, that's equal to 32. 3 does not go into 32, so I can't get 3 times something into 32. However, 4 does divide into 32. 4 times 8 is equal to 32, so that's another factor pair. And at this point, we can kind of keep going. Does 5 go into 32? Well, no. Does 6 go into 32? Not evenly. 7 does not divide evenly. 8 does, but we already have the 8 right here. So at that point, we can kind of stop, and these are the 3 factor pairs that we can get from 32. And this is kind of a easy way to go about it. You can start with a 1 and then start working your ways up with the numbers and seeing how far you can get before you kind of double back to a number that you've already come to. And at that point, you have exhausted all of the factor pairs. Maybe one more quick example. Something like 36. Of course, as we said, we can always take 1 times whatever our number is, and that will be our first factor pair. So 1 times 36 is a factor pair. 2 also divides 36. 2 will go into 36 18 times. And this one, 3, also goes into 36, so I can divide this as well. 3 goes into 36 12 times, so 3 times 12 is 36. That's our next factor pair. 4 also goes into 36, so 4 times 9 becomes a factor pair. 5 does not divide into 36. 6 does, so 6 times 6. 7 does not. 8 does not. 9 does, but we already have a 9 right here. So that tells us that we can stop at this point because we've circled all the way around, because it would be 9 times 4 would be the next one. And then if we kept going up, 12 would be the next one, so we get 12 times 3. However, these already exist on the list, and so At that point we know that we can stop finding our factor pairs. Maybe one more quick example. A little bit larger number, 100. Of course, we can always start with 1 times 100. That will always be our primary factor. 2 times 50. Keep working our way up. 3 does not divide into 100. 4 does. 4 goes into 125 times. 5 also divides into 100. 5 times 20. 6 does not divide into 100. 7 does not also. 8, nope. 9, nope. 10, yes. And then as we keep going up, 11, 12, 13, 14, 15, 16, 17, 18, 19. The next number that divides into 100 on our list is going to be 20, because 20 times 5 is 100. However, we already have 20 and 5 right here. So at that point we can stop. And we know that this is the list of all of our factor pairs. Now certain numbers will only have one factor pair. It would be 1 times whatever number we're starting with. For example, 43. The only factor pair you can get out of 43 is 1 and 43. If you go through the list, 2, 3, 4, 5, 6, you'll never get another number that divides into 43. Numbers that only can be divided by 1 or themselves, that only have one factor pair, we say that these are prime numbers. And as you do more of these, you kind of start to learn which ones are the prime numbers. You can start to know them in your head, which ones are factors, which ones are not. Prime numbers have to always be odd, of course, because an even number can always be divided by 2. The only exception is the number 2, because 2 is equal to 2 times 1. So 2 is technically a prime number, but any even number that's bigger than 2 has to be a non-prime number, because you can divide 2 into it. So now that we know what a prime number is, we can look at taking any number and writing its prime factorization. Now, prime factorization essentially just means take any number and write it as multiplication of only prime numbers. So in other words, we're taking the number and we're factoring it into its smallest parts. I'll show you an example of what I mean. If I take the number 36, I could rewrite 36 as 2 times 18. However, 18 is not a prime number, so that means that I'm not done factoring this yet into its prime factorization, because 18 will factor into 2 times 9. So in fact, I could rewrite this as 2 times 9, because that's what 18 factors into. Okay, so am I at my prime factorization yet? Well, no, because 9 is not a prime number. 9 will factor into 3 times 3. So if we keep going with this, now when we factor 9, that factors into 3 times 3. Now at this point, we're finished, because 2 is a prime number, 2 is a prime number, and then both 3's are prime numbers. So what we can do is actually write 36 as a prime factorization would be 2 times 2 times 3 times 3. And at this point we're finished. Now this is actually a pretty easy methodical way to do this if you create kind of a factor tree. And at each point you pull out a new number to factor. You have to be careful to make sure if you have multiple numbers like I have 2 2's here and 2 3's, that you're bringing them all down at the same time and you're not losing any of the numbers. Now you can always be correct when you can always know that you're correct when you do prime factorizations, because all you have to do is multiply all these numbers back out and make sure you get back to the correct number. So here 2 times 2 would be 4, 4 times 3 would be 12, and then 12 times 3 would be 36. So I know I'm definitely correct on that. So the nice thing about prime factorization is that if you're doing this on an exam or a quiz, you can always double check yourself. If I had multiplied this out and gotten some number that was different than what I started with, that means that somewhere here in my process I made a mistake and I need to go back and redo the process. So let's try a different number. Maybe we'll go a little larger, so something like 45. Again, to start with the prime factorization, just pick a factor pair. Any factor pair will work because you can continue to break down the numbers into more and more factors. So in example, in this case, I know that 45 breaks into 9 times 5. In this case, I stop and I say, okay, are both of these numbers prime? Well, 5 is definitely a prime number. Nothing divides into 5 except for 1 and itself. So 5 is prime, so that's good. However, 9 is not prime. I can continue breaking 9 down. In fact, 9 can be thought of as 3 times 3. So then I bring down my 5, and I have my prime factorization. It's 3 times 3 times 5. And of course, I can double check this. 3 times 3 is 9. 9 times 5 is 45. Now, you might have been wondering, well, what if you did the initial factor pair differently? For example, 45 could also be factored as 3 times 15. That's a factor pair of 45. 3 times 15 is 45. Well, this is fine. You'll still get the same answer if you complete the process, because whereas 3 is prime, 15 will continue to break down. 15 will break down into 3 times 5. And so then I can bring down my 3 here, and you'll see that this number and this number are exactly the same. So when you're doing this prime factorization, it doesn't matter what initial factorization you start with, as long as you continue down through the process, you'll eventually get the prime factorization that you're looking for. Maybe we'll do one more that's a little larger. So the prime factorization of 300. So the first thing, just find a factor pair. It doesn't matter which factor pair that you start with. Maybe the most obvious one here would be that 300 is equal to 3 times 100. Okay. And then we ask ourselves, are these both prime numbers? Well, 3 is definitely prime. However, 100 is not prime. You can divide other numbers into 100. So let's do that. You can divide 100 a few different ways. 5 times 20, 4 times 25. Maybe we'll just go with 5 times 20. It doesn't matter which one you pick, because as you break down the numbers, you'll eventually get to all the smaller numbers that you need to complete the prime factorization. It doesn't matter how you factor at any particular step, as long as you continually factor all the way down and keep breaking apart all of the numbers. Okay, so now at this step, 3 and 5 are both prime. However, 20 is not prime because this can be divided into 2 times 10. It's 20. Okay, 3 is prime, 5 is prime, 2 is prime, 10 is not prime. So again, I can break this down. 10 breaks down into 2 times 5. At this point, we can say, yes, 3 is prime, 5 is prime, 2 is prime, 2 is prime, and 5 is prime. So that means we're done. Now, there's not necessarily a correct order to write the numbers in. Typically, we will write the lower numbers on the left and the higher numbers on the right. So if I were writing down this answer, I might write it as 2 times 2. How many do we have? 1, 2, then 1, 3, and then 2 5s. So this would be a perfectly good way to write this. Now remember, you could also use the old school multiplication sign, but we want to try to get out of this habit if we can, because we're going to start using x's eventually when we're going into algebra, and we don't want to confuse the two. Again, you can check this mentally just to make sure you got it correct. 2 times 2 is 4, 4 times 3 is 12, 12 times 5 is 60, and then 60 times 5 is 300. So that's good. We turn in our exam, and we are 100% confident that we got this answer correct. So that's what's really nice about these. If you have time, you can always go back and figure out where you made a mistake, if you made a mistake. I did mention that the numbers that are only divisible by 1 in themselves, we call those prime numbers. The opposite of a prime number is what we call a composite number. So if you ever hear me use this term composite number, that means it's a number that can continue to be broken down. It's not a prime number. It's the opposite.